The replication lag forecast model provides predictive estimation of data staleness across distributed replica nodes. The system maintains a sliding window of observed replication delays, sampling network latency, disk I/O contention, and write volume at regular intervals. These metrics feed into a linear regression estimator that generates upper and lower bound forecasts for the next reporting period, allowing clients to make informed decisions about replica selection based on acceptable staleness thresholds. The observation window operates on a fixed-size circular buffer of 60 measurement points, each representing a 1-second interval. When a new measurement arrives, the oldest entry is discarded. The buffer stores tuples of timestamp, observed lag in milliseconds, write throughput in operations per second, and disk queue depth. Measurements are collected asynchronously from the replica monitoring daemon and do not block primary write operations. Buffer overflow is prevented through atomic compare and swap operations on the write index. The regression estimator recalculates coefficients every 30 measurement windows, or 900 seconds, whichever comes first. It performs ordinary least squares regression using disk queue depth and write throughput as independent variables and observed lag as the dependent variable. The regression model includes an intercept term representing baseline replication delay inherent to the system topology. Residual standard error is computed and used to establish confidence bounds around point predictions. The forecasting function accepts current write throughput and disk queue depth as input parameters. It applies the fitted regression coefficients to these values, computing a point estimate of expected lag. The function then returns a tuple containing the point estimate, upper confidence bound calculated as point estimate plus 2 standard errors, and lower confidence bound calculated as point estimate minus 2 standard errors, providing a 95% confidence interval. Client applications query the forecast model through the getLagBounds function, passing a replica node identifier. The function returns immediate predictions without blocking. If insufficient historical data exists, the system returns default bounds of 0 milliseconds lower and 5,000 milliseconds upper, ensuring safe operation during model warm-up periods. The warm-up period spans the first 30 measurement windows after service initialization. Staleness bounds are represented as an optional type containing lower MS and upper MS fields. The lower bound represents the pessimistic minimum lag. The system guarantees that actual replication lag will be at least this value. The upper bound represents the pessimistic maximum lag. Actual values exceed this bound only in exceptional circumstances. Clients compare these bounds against their maximum acceptable staleness parameter to determine read availability against specific replicas. The model incorporates adaptive weighting for recent measurements, applying exponential decay to observations older than 5 minutes. Measurements within the decay window receive linear interpolation of weights, starting at 1.0 for the most recent measurement and declining to 0.5 at the decay boundary. This weighting strategy reduces bias from historical periods with different write patterns, while maintaining stability in estimation. Anomaly detection runs continuously on incoming measurements. If observed lag exceeds the upper confidence bound by more than 20%, the measurement is flagged as anomalous and excluded from the regression calculation. Anomalies are logged with timestamp and severity level but do not interrupt service. If more than 15% of measurements in a 30-window period are flagged as anomalous, the model resets and reinitializes, entering warm-up mode. Per replica forecast state is maintained separately, allowing differentiated predictions for heterogeneous replica configurations. Each replica maintains its own circular buffer, regression coefficients, and anomaly counter. Cross-replica coefficient sharing is disabled by default, as topology differences and network topology variations between replicas warrant independent models. An optional shared mode pools observations across replicas with identical hardware specifications, controlled by the enable coefficient pooling configuration parameter. The measurement collection daemon runs at separate OS process priority than primary database operations, ensuring measurement latency does not impact transaction throughput. Measurements are obtained through non-blocking reads from shared memory metrics exposed by the replica process. If the daemon falls behind and the circular buffer fills before a measurement can be written, the oldest unprocessed measurement is silently discarded without triggering an error condition. The getLagBounds function implements caching of computed bounds for up to 1 second, reducing CPU overhead from repeated queries during the same forecast interval. The cache key is derived from the replica identifier and current time bucket. Cache invalidation occurs when new regression coefficients are computed or when anomaly flags exceed threshold. Cache statistics are exposed through monitoring metrics for observability. Confidence level configuration allows adjustment of the standard error multiplier, currently fixed at 2.0 for 95% intervals. Operators may specify alternative multipliers through the confidence level sigma configuration parameter, accepting values between 1.0 and 4.0. Higher multipliers increase bounds width, but reduce false positive staleness violations. Changes to this parameter apply immediately to subsequent forecast computations. Historical forecast accuracy is tracked through comparison of predicted bounds against realized lagged values. For each forecast period, the system records whether actual lag fell within predicted bounds. The hit rate, calculated as a sliding 90-day percentage, is exposed as a histogram metric. If hit rate falls below 85% over a 30-day window, the system logs a warning and enters diagnostic mode, increasing measurement frequency to 1 per half second. The model supports optional manual override through the setForcedBounds function, allowing operators to temporarily specify fixed lag bounds during maintenance windows or known anomalous periods. Forced bounds remain active for a specified duration, defaulting to 1 hour. All queries during forced override mode return the specified bounds regardless of computed forecast. Override events are logged with operator identifier and reason. Serialization of model state occurs every 15 minutes to persistent storage, allowing warm start recovery after service restart. The serialized state includes the circular buffer contents, current regression coefficients, anomaly counter, and model initialization timestamp. Deserialization applies checks to ensure buffer consistency and coefficient validity before restoring state. If deserialization fails, the model initializes fresh without applying historical state. The lag forecast model operates without external dependencies beyond standard system metrics. No machine learning libraries or complex numerical packages are required. The regression calculation uses only basic arithmetic operations, suitable for embedded deployment in resource-constrained environments. Memory footprint per replica is fixed at approximately 40 kilobytes, accounting for the 60-element circular buffer and coefficient storage.